Exactly that. Yeah, it seems to work. I'll- Okay, first of all, thanks to the organizers, Alessandra and Giuseppe, for a wonderful organization. It's been a really wonderful week, fantastic time, beautifully organized. I feel very proud too of all the students who have defended their theses this week. Feel almost like they're my students by now. So, and also thanks to all of you for sticking it out to the bitter end here. So I'd like to talk today about about probability and non-determinism combined in a single system. Probability and non-determinism has a very long and storied history. Of course, probability was first discussed as in the context of computer science, probabilistic programming languages going back to the 1980s. It sort of fell off for a while, but now there's been a resurgence of interest due to machine learning applications and statistical analysis of large data sets. There have been a lot of new programming languages that have been invented, and formalization of probability is the formalization of the preferred one is Jerry or distribution model. Non-determinism, of course, goes even further back. First reference to non-determinism that I know about is in Turing's original paper on the Schrodinger's problem. Then it was received a little bit of a push by Kleene and Rabin and Scott in the 1950s. And the preferred formalization is the power set unit. So there are these two effects that would like to be combined in a single system. And there's been well, I should say a little bit about how these things work. So if you want to model non-determinism as power set, you have a power set monad, which is when you want to combine them propositionally, what you do is you start from a point and you get several output points. Then from each one of those, you see where you can go, and then you take the union of those. That's the multiplication of the monad. That's how power set works. Probability is similar, where you have a distribution. So you start from a point, you get a distribution on your output points, and this is the so-called Jerry monad or probability monad. And the way you compose these things is by integration up the middle. So you take the middle space and you divide it up into infinitesimal sized regions where Q, the second Markov transition, doesn't vary too much over that little region. And then you add those up and take the limit with Lebesgue integral, and that's how you compose Markov kernels. Now, you'd like to combine these two things in a single system, and there is a very long history of people who have tried to do this. This is all the papers that I can find that have some form of probability and non-determinism combined, going all the way back to Barty in 1985. Most of these, in fact, almost all of them, take the point of view that non-determinism is demonic, which means that it's out of the control of the program. It comes from Barty's original paper. So this paper in 85 that he wrote was about concurrency, where the non-determinism is controlled by an outside agent, usually a scheduler, that's figuring out how your different threads are going to interleave, and then your program has to be correct no matter what the adversarial agent does. So it's an adversarial situation. But the point is, the non-determinism is not under the control of the programmer, but under the control of an outside agent, whereas the probability part of it is under the control of the programmer. I'm interested instead in angelic non-determinism, because I would like to use the non-determinism under the control of the programmer to reason in cat style as it's used for Kleene algebra tests and in that kind of equation reasoning. Now, all of these results, if you go through them, they all don't seem to quite work. There's always some kind of little workaround that has to be done because the mathematics doesn't quite work out. And there have been a lot of, this caused a lot of difficulties with these things, and people address it in various ways. But finally it was discovered at some point that the reason it doesn't work is that there is no distributive law relating the two effects. That was discovered by Plotkin, and it was published in a paper of Baraka and Winskell. What do I mean by that? So when you want to combine two effects, ideally, you would like to have a distributive law between them. And what that means is it allows the operators to swap positions. And essentially, it allows you to combine two effects into a single, say, tandem effect. Exactly as it's analogous to the way multiplication distributes over addition. It allows you to transform a product of sums into a sum of products. So you can kind of swap the sums and the products, and you can compose these. You can cascade these things. So you can take any expression of sums and products and multiply it all out and represent it sort of canonically as a big sum of products.
Sorry, and here these two operators would be non-determinism and some form of probability.
Relax, relax. You're way ahead of me.
Binary.
You're way ahead of me. Okay. Okay. What do I mean? So formally, what I mean by a distributive law is this. Okay, so this is just so you know that it's a definite formal thing. There's some axioms that need to be verified to make it work. They're known as the Beck axioms. Here we have two monads represented by functors f and g, and my distributive law is this lambda that allows me to transform an fg into a gf. And there are lots of examples of this, but this is what you have to do. And there's provably no such distributive law. It's provably impossible between the power set monad and the Giri. So, and that is the problem with all of these results that all of these papers that require the workarounds. Okay, but what I want to do today is exploit a very recent discovery of independently by Bart Jacobs and Bash and Staten, that there is a distributive law between probability and the multiset monad. So the only difference is I'm going to go from power sets to multisets. Okay, and you can actually see very plainly how this distributive law works. If you give me a multiset of probability distributions over the same space, I'm going to sample them all independently, and that will give me a multiset of outcomes. And then, and each one of those outcomes occurs with a certain probability. Since I sampled independently, I just take the product of the probabilities of the different samples, and that's the probability of my multiset of outcomes. So what I've done is I've turned a multiset of distributions into a distribution on multisets. That's my distributive law, or that's the Jacobs and Dash and Staten's distributive.
So Dexter, can you say again why considering multisets solve the problem? I think you said it, but I missed it.
I'm going to get to it. Just okay. Come on, guys. Give me a break. I spent a lot of time making these slides. Let me go through. Okay. So I promise you'll get all your answers with that eventually. Okay. So the contributions in this area that we've been able to make with my students, Sean Ong and Stephanie Ma, we had a PLDI paper this year where we built an automaton model and a regular expression definition, and with angelic nondeterminism formalized by multisets instead of power sets, and proved a Kleene theorem between them. They're equally expressive, which is the first result of its type after all this long history. And we gave some sound equational axioms, which we believe are complete. We don't have a completeness proof yet, but working on it, and compositional semantics. Today, I'd like to talk about a relatively new result, which is a decision procedure for the equational theory that comes out of this. Okay, so in order to describe this, let me recap the contents of our PLDI paper so you can see what we're working with. So first of all, our automata that incorporate this angelic nondeterminism look like this. They consist of 4 different types of states. So we have non-deterministic states, which are labeled with this non-deterministic choice operator, which we denote by ampersand. Normally that would be denoted by plus, but I want to use plus for something else. So we'll use ampersand for that. Each state labeled with a non-deterministic choice operator has a finite multiset of successor states. We have probabilistic states labeled with this symbol, and we have a finite distribution on successor states. We have terminal states, skip or fail, or accept or reject as you wish, with no successor states, and then action states labeled with a letter of an alphabet with 1 successor state. We have a productivity assumption which ensures that our semantics is well defined. Every cycle has to have an action state. It allows us to define, give a co-inductive definition of the behaviors of these automata. The operational intuition is we start with a single agent on a start state, and the agents will proliferate. So at any point in time, there may be multiple agents occupying various states of the automaton. At probabilistic state, an agent at a probabilistic state samples the distribution on its successor states to get a next state to move to with some probability, and it moves to that state, that single agent. At choice states, I'm going to split. So this is where the multisets come in instead of the power sets. And this is why actually the mathematics works now, because when you use power set, you forget the fact that you have independent things going on. And now we're keeping them independent by just proliferating agents. So we're going to spawn a new independent agent for each successor state, and each one, we put 1 new agent on each of the successor states. At action states, we scan past, kind of remembering the letter that we saw, and at terminal states, we skip or fail, we accept or reject, and what you're accepting is the string of action symbols that you've seen so far since the beginning. Okay, here's a typical automaton. Here's a probabilistic state. So an agent there at this state S, would sample this distribution to find a state to move to. These are probabilities that you move to the next state. Let's say it samples and moves here. Now this is a choice state, so we'll split and we'll have multiple agents going down each one of these arrows. So you can see that from this state, an agent at this state would accept epsilon, the empty string, with multiplicity 2, with probability p plus r, and would accept the empty string with multiplicity 1 with probability q, and with multiplicity 0 with probability, the remaining probability. So operationally, at any point in time, you can have multiple agents on each state. Each agent acts independently. Strings are accepted with multiplicity. So a typical event that you can test the probability of is observable behaviors are with probability at least a half. Some string is accepted with multiplicity 5, and some other string is accepted with multiplicity 7 with probability at least a half. That's a typical thing that you might want to ask. Languages are not sets of strings anymore, but multi-sets of strings. So the behaviors of a state of an automaton, the behavior is an element of this space, which is the space of probability distributions on multisets of strings with finite multiplicities. Question.
So if the string is accepted with multiplicity 5, can I think of it as 5 agents?
Yeah, 5
accepting
agents.
it?
Yep, 5 agents accepted that string. Yep, exactly right. With some probability, because there are probabilities too going on. So it's
Yeah.
multiplicity 5 with probability 1/2, multiplicity 6 with probability 1/4, and so on.
And it's exactly 5, not 5 or more or something.
You can do 5 or more.
Mhm.
That's also an event, testable event.
Dexter, and it can iterate because you just showed the tree of that two.
I just, that was just a fragment.
Yes,
You
but
can
I mean
iterate.
that it can continue.
Yep, it can continue. Yep. Okay. This is the co-inductive semantics of automata. If, for example, if you have a skip, state is a skip, then it's the multiset associated with that state is the singleton multiset, the Dirac point mass measure on the singleton multiset containing the empty string. Fail, it's the empty multiset, Dirac measure on that. For the non-deterministic choice, that's the interesting one. You sample all of the behaviors of the successor states and take their multiset union, which is the sum as regarding them as functions. It's interesting that the behaviors, we took the behaviors to be probability distributions on multisets of strings with finite multiplicities. This is a standard Borel space. It's an uncountable state space, and in fact, our automata can give you can get continuous measures. Turns out there are examples of that. But an interesting aspect of this is that correlations are significant, right? This is a big joint distribution on multisets. And previously, probabilistic automata, people considered two automata to be equivalent if they accepted each string with the same probability. But that doesn't take correlations into account. And actually, this semantics is a little bit more accurate because it allows you to talk about correlations between different strings being accepted with different probabilities. Okay, it's a big joint distribution. For the special case of binary choice and non-deterministic choice and probabilistic choice, the picture looks like this. So if I have a state with two, this just represents two successors, S and T, with this non-deterministic choice between them. You take the product distribution, which allows you to sample them independently, and then you take their multiset union. So this is the push forward measure of this product measure under the multiset union operation, which is a measurable function. And then probabilistic choice works in the obvious way in the binary case. Okay, we also have a corresponding expression language, and this corresponds to the regular expressions corresponding to this class of automata. I have non-deterministic choice, probabilistic choice, sequential composition, something a little bit more general than a star fixed point, but I'm going to restrict it to be linear recursion, which is restricted this way. 3 variables must occur in tail position, and that enforces linear recursion. So it's not really much more expressive than a star, but I do need to have it in this form. Again, there's a version of the productivity assumption in any fixed point expression. All paths from the root of the term E to a free occurrence of a variable must pass through some action state. And semantics of expression more or less models the semantics of automata, except I have to do it in terms of, I have to give an environment here to interpret the free variables, and so that I can give a semantics of a fixed point. All right, so I'd like to maybe focus again on what's going on here. So this is my my non-deterministic choice. Again, you can independently sample these two distributions and then take the multi-set union of the outcomes. That's the operational view of this. This is the how you would express it denotationally. Operationally, you do the sampling and then take the multi-set union. I can express this in terms of a semantic operation, which I'll also call ampersand, on two distributions, on two coordinated distributions over multi-sets, expressed this way, exactly the same way. So again, intuitively sample them independently and take their multi-set union. That would be the operational view. And we came up with a set of valid equations, which we believe to be complete, although we're not there quite yet. There's a lot of details to check, but I think that's true. But I'd like to focus on this, and this is what our distributive law turns into. So this is our distributive law of choice, non-deterministic choice over probabilistic choice. Now, when you stare at this, you can say, well, it looks kind of like distributivity of multiplication over addition. Looks kind of like that, right? So what if we just generalize a little bit and take signed measures? So now I'm going to depart a little bit from probability measures and take sign measures. And this forms a vector space. So take the sign measures, which, so I'm just allowing events to have negative weights. That's all. And every sign measure is actually a weighted difference of probability measures. And that's what I'm saying here. This is a vector space over the reals, and you can extend the distributive law to sign measures, and now it looks even more like multiplication, distribution of multiplication over addition, right? Well, thinking about this leads you to an epiphany. An epiphany for us, this epiphany was that if you take the space of sign measures with pointwise addition and multiplication given by non-deterministic choice, this is exactly a so-called unital commutative associative algebra, or just a commutative algebra over the reals, or for short, an R algebra. So it's an R module, or in our case, a vector space over R with a bilinear multiplication. And the multiplication is non-deterministic choice. And the multiplicative unit is this Dirac measure over the empty multiset. And even for finite S, if you restrict to finite support distributions with the same operations, this is an R algebra, and it's naturally isomorphic to the polynomial ring R over polynomials over indeterminates S with coefficients in the reals, which is the free R algebra on generators S. And you can see this by observing that finite multisets are essentially monomials, right? I can take this multiset with S occurring with multiplicity 3 and T with multiplicity 2. That becomes this monomial. And multiset union is just multiplication. And I have two different representations here, the finite multisets with multiset union and the empty multiset. And this monomials over S with multiplication and 1, these are isomorphic representations of the free commutative monoid on generators S. And then distributions, sign distributions are just weighted sums of these things. So what that says is that not only is the distributivity of multisets over distributions analogous to the distributivity of multiplication over addition, it is the distributivity of multiplication over addition, which is was quite a revelation for us. Okay, so what can we do with this? So this leads to a decision procedure. And I want to describe, I think I can give you all of the ideas in this decision procedure and to the point where you will understand it completely modulo the details. The basic intuition is to mimic the algorithm for the equivalence of weighted automata. So there's a very nice efficient algorithm for deciding whether two weighted automata over the reals, let's say, are equivalent. It's based on linear algebra. And the way it works is it inductively computes the so-called forward space of a difference automaton. I'm going to tell you what those things, those terms in red, I'll tell you what they mean. Inductively computes the forward space of a difference automaton, and the termination of the algorithm is based on a dimension argument because we're in a finite dimensional vector space, and dimensions can only grow finitely many times before they have to terminate. And for us, we're going to do almost exactly the same thing. So our decision procedure is parallels this algorithm for weighted automata very closely, except instead of flat things with linear algebra, we're now going to use polynomial algebra. Okay. So linear algebra becomes polynomial algebra. The forward space, instead of a subspace, subvector space, will be a polynomial ideal in some polynomial ring. And the termination is based on the Hilbert basis theorem, which is, again, a dimension argument. Okay, so let's see how this works. So going back to weighted automata, if you recall, a weighted automaton over, let's say, the reals, or you can do this over any ring, but let's say the reals. So it's going to be a tuple consisting of a set of states, an input alphabet, a transition function, which I'll call D, a beginning vector alpha, and a final vector, which I'll call eta. So finite set of states, input alphabet, transition function takes a state and an input letter, current state and a letter, and gives you a vector of a weighted vector of states to go to. There's an initial vector, which is just again, a weighted vector of states, and then a final vector. And the way these things work is you take the transition function, which when you specify the automaton is best to think of it as given an input state and a current state and an input letter gives you a vector of next states to go to. I'm just going to recurry that by moving the S up to the exponent. So then I have express D as a map from input letters to matrices or linear maps over S with the rows and columns of my matrix indexed by S, the set of states. Extend that to a monoid homomorphism uniquely. This is the free monoid, so this extends uniquely where over here the monoid is just matrix multiplication, okay, or composition of linear maps, and done this way inductively. And the behavior of the automaton is the rational power series. It's going to be a linear combination of, or a rational power series over strings. So a real weight for each string, where the weight of the string X is start from the initial vector, hit it on the right with the transition computed for x, and then take the inner product with the final vector eta. And that gives you a real number, and that's the coefficient of x in this power series. So that's how weighted automata work. Here's the picture. So you think of the input vector as a row vector this way, just take the transpose to make it a row vector. Given the input x, you calculate the product of the transitions for each letter of x, and you get a row vector, and then you take the inner product with the final vector eta, and you get a real number, and that's the value of x. It's a real number. Okay, now the nice thing about, since we're in a vector space, the nice thing is that we can subtract, which we can't do normally with ordinary automata, but since we have the real numbers, we can subtract. So you can compute this difference automaton, which works like this. You can take two automata, let's say I have two automata, M1 and M2, and I want to decide their equivalence. The equivalence, they'll be equivalent if the difference automaton always gives you 0. Right? The difference is going to give you 0. So what you do is you start with the start vectors, you negate one of them, and then you form this block diagonal matrix here. And the definition is the definition of this is like D3, this whole matrix, and the definition of D3x is just multiply this by itself, again, according to x. And then two automata will be equivalent if the difference between for each x, if the difference between the two coefficients of x are the same in the two formal power series, and that's if the forward space, which is this space, is orthogonal to eta 3. This is eta 3, the whole two things together. Okay, so the nice thing about this is we can subtract, and that makes it easy to check equivalence. Okay, and the way the algorithm goes is we have the forward space, which is this subspace of r to the s, consisting of all of the vectors that you ever get for any x by starting from the initial vector and applying d sub 3 of x for all possible x. Those are all the possible states you can reach. But this set of vectors those are the ones we're interested in. They span a space, and that space must always be orthogonal to eta 3. So if the two automata are equivalent, any vector in here in the space spanned in the forward space will be orthogonal to eta 3. Okay, so we'll start with start vector, and that's this. And at stage n, let's say we've calculated the forward space up to n. That's a subspace of the orthogonal complement to eta 3. We check that all the basis elements. We don't have to check that these elements are orthogonal to eta 3. Let's say we have the basis for that space. Just check that the basis elements are orthogonal to eta 3. Even though this is an infinite space, it's got a finite basis because it's a subspace of r to the s. Check that all of the basis elements are orthogonal to eta 3. If so, apply dA to all the basis elements. That's all you need to do. And then see if you go outside of the space, see if you get anything new. If you do, calculate a new basis and keep going.
So
If you don't, that's all right.
do you calculate the basis using gram something?
Yeah, Gram-Schmidt, if you like, any way you like. It's just linear algebra. If you do not get anything new, then you will never get anything new, because the dimension has to increase if you get something new, and it can only increase finitely many times because we're in a finite dimensional vector space. So eventually this is going to terminate. You're not going to get any, either you find something that is not orthogonal to eta 3, in which case you fail, or you always get things that are orthogonal to eta 3. Eventually you don't get anything new, and the first time that happens, you can stop and say we're done. the two automata are equivalent. Okay, that's the whole algorithm. If you understand this, then our algorithm parallels this exactly. Okay, except instead of flat things, we're now doing curvy things. Okay. So the decision procedure for probabilistic Kleene algebra is the same, except instead of R to the S, we're now in the polynomial ring R adjoin S, or R, the polynomial ring with indeterminates S. Linear algebra becomes polynomial algebra. Again, this is the relationship. Instead of orthogonality testing, okay, we're going to do ideal membership testing. So we're going to use Grubner basis algorithms for doing that, Grubner basis technology. And the termination of the algorithm is also a dimension argument. It depends on the fact that this space, this polynomial space, is Noetherian, which means that there is no infinite ascending chain of ideals. All ascending chains of ideals in any Noetherian space are finite. That's the definition. And the polynomial ring satisfies that. That is the Hilbert basis theorem. So we use that to ensure termination. Okay, so here's the decision procedure for probabilistic Kleene algebra on one slide. Given the two automata, so these are now automata of the form that I showed you earlier with non-deterministic choice and probabilistic choice. Construct the difference automaton M3. You can do the same thing. We can subtract because we're in polynomial land now, which allows subtraction. Forward space of M3 will be an ideal in R of S, would be that polynomial ring. And the two automata will be equivalent if the forward space is contained in the ideal of polynomials that vanish at this point where I'm assigning one to all of the states. What that does is essentially prunes the tree, prunes the computation tree, makes everything fail after some point. At stage n, say we have a Grubner basis for the forward space. We check that all the basis elements vanish. That's a necessary condition. If any of them do not, we immediately fail. And we can check that they vanish. But you can just plug in one and just evaluate. That's easy to do. If everything is still orthogonal, we advance M3 by one step for each input letter, the same way that we did before for weighted automata and each basis element. And if we get something new, something outside of the ideal we have so far, which we can check, Grubner basis allows us to check that. Ideal membership testing is decidable. We can check that with Grubner basis. If we get something new, we can calculate a new Grubner basis. If we don't get anything, and check that everything is still vanishes at one in every step. If we do get something new, we calculate a new basis and keep going. If we don't get anything new, we're done for the same reason as before. We have the basis for the ideal. We're never going to get anything new. So generates the entire ideal. So the same thing happens. Okay, so that is, and then it's guaranteed to terminate by the fact that the space is Noetherian. Okay, so that's our decision procedure. So the next steps, what we'd like to do, well, you could do a complexity analysis. Actually, I don't think this is worth the effort because it's going to be really bad. Polynomial ideal membership testing is already, I think, exponential space complete. So I don't think it's worth doing a complexity analysis for this algorithm. It's just not going to be very good. But I think there is hope for if there's going to be a special case where it's going to be much more efficient. I think once we add tests and do a guarded version like happens with GCAT, there's this version of Kleene algebra with tests of CAT that is guarded. It's called GCAT, and Even though cat equivalence of cat formulas is p space complete, equivalence of GCAT formulas is almost linear time. It's n alpha n, where alpha is the inverse of Ackermann's function. So very, very efficient. And I think similarly, analogously, we will get a speed up here because having a guarded version mitigates the proliferation of agents that cause the complexity blow up for PKA. I'd like to relax the productivity assumption. I think you can actually give a semantics and an algorithm without that assumption. We did it for convenience. It allows you very nice co-algebraic definition of things and unique fixed points because it's with the productivity assumption, you get a metric and the behavior equations give you a contracted map, which has a unique fixed point by the Banach fixed point theorem. But I think that assumption can be relaxed. And most importantly, I think one can get a completeness proof for the axiomatization we gave. Okay, that's it. Thanks.
Questions? Yeah, thanks for a very beautiful talk.
Oh, thanks.
But my question is maybe in the direction of application. So if you do all the things you want to do on your concluded slide, like in terms of using this to build software tools for kind of verifying maybe some properties of some systems, like where could we go with that?
Well, people have been trying to do this for a while, and I think you could do quite a bit with it. So having probability is nice. Having a Kleene theorem is nice. So you have this automaton model and the regular expression model. You can use regular expressions for have gazillion applications, but now you can add probability to that if you like. So you can reason in probabilistic context. I think it might be very useful. Probably a lot of things that would be interesting to look at to see what you can model. We have this system for network verification called NetCat, and we have a probabilistic version of that, and that's already proved to be quite useful in verifying. Like you'd like to measure expected uptime of your network. You know, what is the probability that some component is going to go down? What is your expected time between failures, sort of thing? What is the expected time of delivery of packets? People have done analyses like that.
Yeah, and this new technology would give you what kind of new properties to verify?
So all of this this connection with commutative algebra was not available even to us when we did our first paper. So that whole PLDI paper that I talked about at the beginning of the talk, we didn't know about this connection to, it wasn't available to us. It wasn't available to Dash and Statement. It wasn't available to Jacobs. They did this separately if they had known this connection, everything would have been much easier. And now in retrospect that we know about this, I think it's a very rich mathematical environment to work in, and I think we can exploit that I'm hoping we can get completeness pretty soon, and if anybody here is interested in hacking on it, I'd love to work with you.
Yeah, thanks. Wonderful talk. I understand that you have to go in this direction, not just because it's great mathematics that's classical and polynomial. Arithmetic works very well, but because of this distribution law not holding when you do the original stuff. But we looked at what happens if you try to cut back down to the power set model, because maybe you don't need that additional information, right? And you're maintaining it right now.
Yeah.
Throughout the whole algorithm, and you get more efficiency if you having this insight now try to design something that actually works for the power set.
That works for the demonic case as well as the angelic case. I haven't really thought about that, but people have looked at special cases that do work out nicely, but they have to restrict things. So usually either they use a restricted distribution law, or they don't allow distribution at all, or you can do distributivity in the other direction, but you have to add sort of non-constructive power to the daemon. You have to, they can do anything in the convex closure of what's allowed by the syntax, which is kind of a non-constructive thing. So there are a lot of things that people have done to try to work around this lack of a distributive law. And some of those have been quite successful. And that list of papers that I gave at the beginning, and I have to confess, I'm co-author on some of them too. So I know how bad it is, but yeah, it's there are some good things you can do. It's not all bad.
Sure, because now you have this much better perspective, but you can maybe explain why some of these ad hoc decisions were either bad or good.
Well, I don't know if I can do that. It's a pretty complicated situation, but I can explain why what the multi-sets buy you over the power sets. When you go to power set, pardon me, when you use power sets, you lose information. That makes the mathematics not work. When two agents land on the same state so you can think of an agent with a stash of bits that it's coin flips that it can consult when it needs to make a probabilistic choice. And you can think of a single agent moving around, and maybe it's making non-deterministic choices too, and it can go here or it can go here. And then if it goes over here, it makes a probabilistic choice using the same bit that it would use if it went over here. And you might think that's okay because it's not using the same bit for the same probabilistic. It's using the same bit, but they're different probabilistic choices, and they're in different places. But no, they have to be independent to make the mathematics work. You have to maintain the independent. You have to remember that information. So the multi-set version allows you to remember information that shouldn't have been forgotten. I think that's the main idea that I can think of. Yeah.
Yeah, there's a very small comment. I once checked, I think there is no agreed definition of infinite multiset. So when one says multiset, it's somehow always finite. You might check it because you stress finite. It's kind of embedded in
So the problem, one problem is if you allow finite multiplicities only, it's not a monad. So the you can take finite multisets with finite support, that's a monad. Or you can take infinite multisets, but then you have to allow infinite multiplicities in order for it to be a monad. So if you just take the natural numbers as multiplicities plus an infinite element, you can make a monad out of that. And that's the one I'm talking about when I talk about.
So it's a limited.
Yeah, just add an infinite element to the natural numbers and allow that to be.
Yeah. Okay. So then we agree because arbitrary definition becomes very weird.
Yeah, it's very weird. But the problem is if you take infinite, an infinite domain and finite multiplicity, it's not a monad.
Okay, and the other is that I think there is a very important algorithm which falls into the category you described, which is backpropagation, which is the main algorithm in the these nets which are studied by all these ChatGPT programs. Now the name escaped to me. The deep networks, yes.
Garlic, crucifixes. I don't do ChatGPT.
I just say that there is a backpropagation algorithm, and it has two features. One is nondeterminism. When there is something, you backpropagate the weights. And there is a non-determinism because you sort of do steepest descent, but you have non-determinism. But you also have a problem of probability because the issue is to reach a minimum, but you can end up in a local minimum, and then one does some stochastic change to kick out the process from the local minimum. So you have both components there.
Yeah,
And I'm
good.
talking only about the algorithm.
That might be an interesting application.
And I really think it is a kind of almost a model example of a program which would fit it.
Yeah.
I will send you a page from a paper where it is just one slide saying this algorithm.
Okay, sounds good.
Jeff Hinton's idea is
Sorry?
Jeff Hinton's idea in the 80s is back.
Yes, but I mean, it is now well written as a one while.
Yeah, thanks for the talk, very interesting. I was wondering that the power set case and the multi-set case, they can be both seen as special cases for formal power series over some semi-ring, right?
Right.
And then the question is, do you know for which semi-rings the distributivity works and for which it doesn't? Is there a characterization?
So we get, so that,
You said something about recoverability of information, right? So that
Yeah.
no information is lost.
Yes.
Could this be formalized or formulated as a semi-ring
maybe,
of sorts?
maybe. I know some people have looked at things like that.
Okay.
Yes, maybe so. Maybe you could do some characterization. So you're saying you want to just generalize from the reals.
Mhm.
Yeah,
Well, not so much from reals. I mean, in one case you have that the semi-ring is the Boolean semi-ring, right? And
Yeah.
that's give you the set case, and for multi-sets it's just a natural.
yeah, you just like to take semi-rings.
Yeah. And then the question, so and for the Boolean doesn't work, you showed, and for
Yeah.
the naturals it works. And so the question is, what?
Yeah, good,
Can we have a more general?
good question. Can you axiomize the semi-rings for which you get it?
Yeah. Property.
Yeah, that's interesting. I don't know the answer.
Okay.
Yeah.
Okay, let's thank Dexter. Thank you. We'll take a 5 minutes break for bathroom and coffee, and then Alexander.
Stop share. Yeah, no problem.